Hi everyone, welcome to this session of 5G World, Service Provider Address on the topic VRAN a 5G Game Changer. My name is Jahid Masud and I'm the head of the radio systems in the Norwegian mobile network operator ICE. So let's get started. Now let's look at the contents we will be covering in this session. We first introduce VRAN, then we take a look at the VRAN architecture in 5G perspective. Then we discuss the drivers and challenges of VRAN. And finally, we talk about a few cases to see how VRAN helps realize some of the most important visions of 5G and whether it can change the game. So what is VRAN? In order to facilitate the answer, let's first look at how a traditional RAN would look like. Traditionally, the radio access network, or RAN, of a 3GPP based telecoms network consists of a distributed network of base stations. The main components of the RAN are the RRU placed up near the antenna in the mast or pole, and the BBU normally placed at the bottom of the site, typically in a site room. These two components would be connected by a fiber, and the whole thing would be connected to the core network via the backhaul network. Now, these two RAN components in the base station comes from a single vendor with hardware and software tightly coupled as physical network functions, or PNFs. RAN software runs on purpose-built hardware from the same vendor. Hence, there would be no disaggregation between RAN software and hardware. However, in VRAN, or virtualized RAN, the network would be transformed to be disaggregated in terms of hardware and software. RAN components now run as virtual network functions, VNFs, or container network functions, or cloud native network functions, CNFs, on commercial off-the-shelf hardware. You see here virtualized distributed unit, DU, or virtualized centralized unit, CU functions running on commercial off-the-shelf COTS hardware. Various virtualization techniques or models are applicable. We could use VNFs using the NFV MANO architecture. The VNFs can run on the containers can run on VNFs, or containers can run on bare metal. In this slide, we say a few things about a typical 5G RAN architecture from a VRAN perspective. In this centralized architecture, radio interface protocol layers, which is shown here, are split onto different radio functions, which can be geographically distributed in different locations. The lowest functions stay at the remote radio unit, or RU, at the cell site, which is a PNF. The rest of the upper layers are divided in DU and CU. DU typically would be centralized in an edge data center, serving several cell sites connected to it by fibers, running eCPRI, running fronthaul protocols like eCPRI and lower layer split option 72X. Top two layers, RRC, PTCP, and STAP, reside in the central unit, which can be located deep in the regional or central data centers. Mid-haul network would connect the CU to the DU, which is defined by 3GPP as F1 interface. CU could be further divided into control plane functions and user plane functions in order to have the benefits of a CUPS architecture. CUPS architecture being control and user plane separation architecture. CU connects the rest of the VRAN network back to the core network. Now, in a VRAN scenario, all these network functions, or radio access network functions, except for RU, are virtualized or containerized, running on top of any commercially available x86 hardware. The orchestration layer manages the instantiation, scaling, and management of these VNFs or CNFs in an automated and dynamic manner. And it can also span towards the virtual core functions. Drivers for VRAN. So before we go to the list of the drivers here, let's get a little bit of a history lesson. 1G and 2G networks back in the 80s and 90s were mostly about voice services. With 3G and 4G networks, we first see data turning out to be the main usage of the network. Now, 5G comes with the promise of a paradigm shift with a plethora of new use cases like enhanced mobile broadband, massive IoT, ultra-reliable low-latency communication services, to name three of the most important of them. These new use cases are fundamentally different, and each of them requires different architecture of the network. However, we cannot build separate networks and infrastructure to support each of these use cases. That would be too costly. We rather use a single network infrastructure in a dynamic and virtualized way to cater all these services. This is called the so-called network slicing, and VRAN coupled with vCore would be critical to achieve this. This is the first driver for VRAN. In addition, we can name some other important ones like efficient scaling and pooling of the network resources, automation for optimized performance, flexibility, and cost efficiency. We can come back to some of them later. In order to support new use cases and achieve efficiency and scalability, we see that RAN functions are now moving towards or expanding towards the central data centers near the core functions. And in a similar and opposite manner, the core functions are expanding towards the edge locations near the RAN functions. Now, VRAN will certainly come with some challenges too. I mentioned four of them here. Firstly, competence. Since with VRAN, the RAN nodes would no longer stay simple and monolithic anymore, they would add a lot of complexity to the RAN. The RAN engineers now need to develop competence in various IT and infrastructure fields. Second, security. The more complex the network, the more vulnerable it is for security. Third, fiber. 5G network is expected to deploy the centralized architecture more and more, which means a lot of fiber needs to be deployed from the edge data centers to the cell sites to run the front haul from the DUs to the RUs. And these fibers could be 20 to 30 kilometers long, as shown here in this diagram, which could be a challenge for most of the operators. Lastly, since the VRAN coupled with the centralized architecture comes with a paradigm shift in the architecture, in the network architecture, keeping up with this with the right mindset could be a challenge. Now let's try to see how VRAN can be critical for realizing the 5G vision. In other words, whether it can be a 5G game changer. We first look at the end-to-end network slicing a bit deeper. One of the main purposes of the edge data center is to allow millisecond level latency by moving some of the core functions at the edge, for example, the UPF. On the contrary, the eMBB service needs high capacity and does not need this low level of latency. Hence, the UPF for the eMBB use case is better to stay at the central data center. Now, the flexible architecture of the VRAN allows or enables the DU to break out the URLLC service to the CUP located at the edge, while the DU uses the CUCP located at the central data center for the eMBB user. In both cases, the CUCP located at the central data center controls the CUUPs. Next, we can have a look at the case of dynamic scaling. In traditional RAN, Hardware resources are fixed and static. As you can see here, at a moment in time, some BBUs are fully loaded while others are underutilized. But after the VRAN transformation, the VRAN architecture allows for dynamic scaling of the network resources as needed. The orchestrator continuously monitors the CPU load and the PM KPIs via the Element Management System EMS. When some threshold crosses, the orchestrator sends commands to the virtualization platform to scale in or out necessary resources for the VRAN functions. Here we see the VDUs getting scaled in or out. This way, we ensure the resources are fully utilized in an optimized and automated dynamic manner. One of the very critical visions for 5G is the automation. VRAN architecture facilitates automation in various ways. For example, VRAN architecture enables IT-grade microservices architecture for RAN functions, which is the key for intelligent automation for RAN functions. Artificial intelligence and machine learning introduce an advanced control plane which can deliver non-real-time and near real-time performance enhancement for RAN functions. Zero-touch commissioning of cell sites has been shown to be achieved within minutes. These are of course only a few of the possibilities. There would be many more that the VRAN could enable as the technology matures. The last case I'd like to talk about is the flexible architecture allowed by the VRAN. So far, we have talked about the centralized architecture, which can be referred to as the edge cloud model, where the RU is located at the cell site, DU at the edge data center, and CU at the central data center. This architecture could be suitable for dense urban type environments. Another model could be what I call the cell site DU model, where the RU and DU are co-located at the cell site connected to the central data center via the mid-hall. This architecture could be good for small cells. VRAN also allows for a traditional model where all the RAN functions are co-located at the cell site connected to the central data center via the backhaul. This architecture could be suitable for remote locations, for example, rural environments. So there you go. In conclusion, I would say that VRAN is a key architecture which is very critical for 5G visions to be successfully implemented. Very soon, we expect to be able to see all these visions realized. Thank you very much for joining this session.